Hi, I'm Deb Ness, and today I'll be talking to you about nuclear chemistry, its relation to the energy industry, the big ideas of chemistry, as well as the universal apostolic preferences. So, what is nuclear chemistry? Well, nuclear chemistry is the study of nuclear reactions. Those reactions can include radioactivity, nuclear processes such as fission and fusion, transformations of the nuclei, such as losing or gaining protons and neutrons, as well as many other things. While there is a stigma around nuclear chemistry due to incidents such as Fukushima, Long Island, or even the bombs being dropped on Japan, nuclear chemistry is a different beast than most think. It has many applications in the medical and energy world, such as treating cancer or providing energy for millions of families across the world. Furthermore, nuclear chemistry is a field of research that, with more studying, has great potential to improve the lives of many. Most importantly, nuclear chemistry has the potential to save the energy industry. The current energy industry is dominated by fossil fuel companies, which are corrupt as well as hurt the environment. There are certain stigmas around nuclear energy. We can change that by instituting many more nuclear energy facilities, which can turn around that issue, as well as save the industry. As of now, the technology that used to fuel the nuclear industry is being tossed out for new and improved technology, such as mini reactors, which are smaller, more efficient, and can power thousands of homes with a single block. Overall, nuclear energy is actually safer than fossil fuels, contrary to what many people think. It has little to no emissions, which is a completely different story from the fossil energy industry. Furthermore, it's computer controlled, well, at least the new technology is. This means that it can be completely shut down by a computer that can sense any single issue within it. The incidents that happened on Fukushima, Chernobyl, etc., those are all due to human error. This completely negates that. Furthermore, Russia and other countries have been using thorium reactors. These are safer, they emit less plutonium, which can be used as nuclear warheads, and overall, they produce just as much energy at less cost. With all of these benefits, it's the obvious choice for the future of the energy industry. We'll now be talking about nuclear chemistry in relation to the big ideas of chemistry. So, a quick overview. The four big ideas are scale, proportion, quantity, which goes over macroscopic and atomic scale, as well as the relationship between scales. Structure and properties, which talks about the properties on the macroscopic scale that are a result of the microscopic scale, which is pretty much just the relationship between the large and small levels. As well as transformations, which is just the transformation of matter, which in the case of nuclear energy is radiation, changing elements, etc. And then finally we have energy, such as distribution of energy, as well as entropy and enthalpy. So, first up, we have scale, proportion, and quantity. When you're considering the macroscopic and atomic scale for nuclear chemistry, you have to realize that all items present on the macroscopic scale are the result of the atomic scale. Any background radiation which you can detect with the Geiger counter and is present on almost every molecule is a result of nuclear chemistry. When an element changes into another element due to decomposition or radiation, that's nuclear chemistry. These are all due to what's happening on the atomic level. That can be any interaction between neutrons, protons, and electrons. And as I said before, that can result in new elements, or even small things such as splitting an atom or fusing an atom with another can result in massive implications on the macroscopic scale, such as a exorbitant release of energy, which is what you see in an atomic blast. Those are both very close relations between the scales, and as you can see, they're very closely intertwined, and you can expect anything that you can see on the macroscopic level that you've seen in nuclear chemistry to be present on the atomic. So, next up, we have structure and properties. This is properties on the macroscopic scale that are a result of the microscopic scale. This seems very similar to scale, proportion, and quantity, but it's sort of different, but it's also the same. For example, we have the release of energy due to fusion or fission. This is what's happening on the atomic scale. You have an atom being either split or fused together with another. This is a single atom. It's impossible to see, but there are great implications with the structure of the macroscopic scale. A release of energy that provides an air blast, heat, etc. Just energy being released, that's the main thing. But then we have radiation. And radiation due to decay is the main type of radiation you see. This is because you have an unstable atom. As you can see in the chart, you have an atom that is radioactive, and it releases a particle and energy, which is radiation. It does this in order to stabilize itself. It usually changes isotopes or elements as it does this. Next, we have transformation of matter. This is a change in the element due to loss of a proton or a neutron, as well as collisions resulting in new elements. For example, in the graph shown, we have nuclear fusion. A lithium-6 and a deuterium atom collide. They form a new element, which then divides itself into two alpha particles. What you see here is fusion, and this results in different elements, as well as a great deal of energy. That's a transformation of matter, as well as a transformation of the energy type, because you're breaking bonds, etc. Transformation is also seen due to radioactive decay. Scientists such as Marie Curie originally saw this when they noticed that elements were changing into new elements as they detected radioactive emissions coming from them. They eventually figured out that in order to stabilize themselves, they were changing into different elements in order to have the amount of protons or neutrons to have an equal amount of electrons to balance them out. Finally, we have energy. If you think about it, nuclear chemistry is all energy. You have radioactivity, nuclear fission, and fusion. All of those can be rated to energy. For example, you have the distribution of energy. In nuclear chemistry, energy is derived from the interactions of subatomic particles. That is, for example, the attraction between the electron and the nucleus, etc. When you break these bonds, such as splitting an atom, you release a great deal of energy. And the distribution of energy in nuclear chemistry is constantly changing, cycling between different patterns in order to change elements, fuse, many other things. The next part of energy is entropy and enthalpy. Entropy, in a way, is the degree of chaos in the universe. If you look at the diagram, you'll see a deuterium atom and a tritium atom fusing in order to create helium and an extra neutron. In a way, when atoms fuse, they increase the amount of chaos in the universe, because there's different combinations they can form, which is chaos in its own way. Then you have enthalpy. Enthalpy is the thermodynamic equivalent to the total heat content of a system. In systems such as fission and fusion, the enthalpy is usually negative, as they're losing massive amounts of heat. In fission, for example, while you're only using a small amount of energy to split the atom itself, it releases an amount of energy much greater than what you use, which results in the fireball and the massive blast that you see when an atomic bomb is dropped. In fusion, however, the enthalpy would be different, as you're using massive amounts of energy in order to heat up the atoms to millions of degrees Celsius so they have enough speed and energy to collide and fuse together. Consequently, the amount of energy lost by the system, while it is still large, is much less than it is for fission. Since we've reviewed the big ideas of chemistry, I'd now like to talk about the universal apostolic principles, or specifically one of them, caring for the earth. When considering energy use, you want to use the thing that's best for the earth. In this case, it's nuclear energy. Because of the way it's done, nuclear energy has little to no emissions, which means a lesser impact on the earth and its atmosphere. Furthermore, it has little to no waste in comparison to alternatives. Every year, over 35 billion tons of fossil fuels are burned in order to create energy. However, in all of the years that it's been used, in the USA, which is the largest user of nuclear energy, we have only 90,000 tons of nuclear waste. This can be easily stored on a couple hundred acres and is much safer than the amount of carbon that goes into the atmosphere. Furthermore, that amount of waste can be greatly cut down by the use of things such as thorium reactors, which produce much less nuclear waste. In addition to producing less waste, nuclear energy also provides much more energy for the amount of resources used, which means that we don't have to use as much of the resources given by our Earth in order to survive. So, to conclude, I'd like to just go over how nuclear energy can save the energy industry. As we've talked about over the course of this video, nuclear energy has many benefits. It's safer, it's better for the environment, it makes less waste, it makes more energy, etc. However, that may not be all. With greater study, nuclear energy has the potential to create many more life-saving opportunities for our Earth. As of right now, we've achieved fusion. The issue is, we need to find a way to create excess energy from the fusion. So, scientists are using machine learning in order to figure out a way in which we can do that. Fusion would create much more energy than fission does, or any other way of creating energy, as well as it has pretty much no waste, as its waste product is helium, which is inert. However, as I said before, this is only the tip of the iceberg. There is many more possibilities for things that can be understood and discovered, with just more funding and more time to work on it. But we've already made so much progress with mini reactors that are computer controlled and thorium reactors, as I've already talked about. The benefits are undeniable. And I think if we can get rid of the stigma that surrounds this industry, we will be able to save the energy industry, save the Earth, and maybe even expand beyond our Earth. This has been Devin Hess. Thank you very much.